This is my submission for the British Computational Physics Challenge on projectiles. I use NumPy in all the challenges, starting with a simple dragless trajectory. Then, in a more analytic model, I also include the point of max height of the projectile. Next, for an input target and launch velocity, I plot the high ball and low ball trajectory, as well as the minimum launch velocity trajectory. Here, for an input launch velocity, height and angle, a trajectory compared to one which maximizes horizontal range with the same launch velocity is plotted. By plotting the high ball, low ball, minimum U and max range trajectories with the bounding parabola, we see the area in which the input target can be reached given the launch velocity and height inputs. This is a continuation of challenge 4, where we use integration to calculate the distance travelled by a projectile with input trajectory and one which maximizes horizontal range. In this one, we're comparing trajectories which have different launch angles from the origin. I set my Y limit based on the maximum height of the projectile with the largest launch angle and created a time array based on the time taken for this projectile to reach the negative Y limit. If we plot the range of the projectiles with time, we notice that for larger angles, they pass through local minima and maxima. For challenge 8, I plotted a bouncing projectile. I use a loop that breaks at the 6th bounce, and as a mini extension to this, I made an animation. Finally, by using a Verlet method, I plotted the trajectory of a projectile which incorporates drag and compared it to one which doesn't. As an extension, I made a 3D plot of a football being kicked, one with the Magnus effect and one without. The inputs for this are the velocity after being kicked, the elevation angle, and the angle off a straight shot. Here are two views of my 3D plot, and here is the real-life example of the Magnus effect. Thanks for watching.